Today we are going to discuss about the stability of the coordinate compound. Next topic, stability of coordinate compound. Now the stability of coordination compound can be explained by knowing their stability constant. स्टेबिलिटी कांस्टेंट पता करने से अपने को पता चल जाएगा कि ये कोऑर्डिनेट कंपाउंड कितना स्टेबल है. इट इज़ गवर्न बाय मेटल एंड लिगैंड रिएक्शन. Interaction. Okay, in this, metals serve as electron pair acceptor, while ligand as Lewis base, since it's electron donor. The metal-ligand interaction can be realized as the Lewis acid and Lewis base interaction. Stronger interaction, greater is the stability. Of the complex. Consider the equilibrium for the metal-ligand interaction. समझो ये रिएक्शन है. It will gives this type of reaction. Okay, where this A is A and X is these denote the charges on the metal, ligand and complex. Charges on metal, ligand and complex. Charges on metal, ligand and complex. ठीक है, तो हम लोग ये लेंगे at equilibrium we can write down this reaction concentration of product, active concentration of product minus active concentration of ठीक है. Stability of the complex can be explained in the terms of K. It is explained in the terms of K, stability constant. Higher the value of K, larger the value of K, larger the stability. Larger value of K, larger is the stability. Okay, the equilibria for the complex formation with corresponding K values are given. For the AgCN complex, K is equal to 5.5 into 10 raised to power 18. K is equal to 2 into 10 raised to power 27. And for this complex, K is equal to 5 into 10 raised to power 33. From the above data, uh, these have a more high value, it is more stable than this complex and then this complex. Factors which govern the stability of the complexes. Factors, which are the factors which govern stability of the complexes? First, charge to size ratio of the metal ion. Charge to size ratio of metal ion. Higher the ratio, greater is the stability. For the divalent metal ion complexes, their stability shows the trends. This is the trend for like this. The above stability order is called Irving-Williams order. Irving-Williams order. In the above list, both Cu and Cu have +2 charge. However, the um, ionic radius of Cu is 69 picometer and that of Cd is 97 picometer. The charge to size ratio of the Cu plus 2 is greater than Cd plus 2. Therefore, Cu plus 2 forms a more stable complex than this Cd plus 2. Okay. Now, second point is nature of ligands. Nature of ligand. First point, the charge to size ratio of the metal ion. Second is the nature of the ligand. Second factor that governs stability of complex is related to easily, how easily ligands can donate its lone pair of electrons to central metal ion. That is basicity of the ligand. This is the basicity of ligands. The ligands, those are stronger bases, tend to form a more stable complexes. More basic, more stable. More basic ligands, more stable is the complexes. More stable is complex. Now, there are some theories. There are some theories which gives the bonding in complexes. From those, one of the theories, valence bond theory. One of the theories, valence bond theory. It states that hybridized state is theoretical state that describe how complexes are formed. The hybrid orbitals neither exist nor can be detected spectroscopically. These orbitals, however, help us to describe the structure of coordination compound. Structure of coordination compound. Okay, so first point is that metal ion provides vacant d orbital. Use a vacant d orbital. Vacant d orbital. Metal ion produced vacant d orbital. और बोल सकते हैं हम लोग vacant d orbital along with s and p orbital of the metal ion can take part in the hybridization. In hybridization, vacant d orbital and s and p orbital can take part, and the number of vacant orbitals formed is equal to the number of ligand. That is equal to number of ligands which can donate the electron pair to the atom. Central metal arm. Overlap between vacant orbital of the metal. Overlap between, this is the vacant orbital. Vacant d orbital. Vacant d orbital of the metal and filled orbitals. Filled orbital of ligand lead to formation of the metal ligand coordination bond. Metal ligand coordination bond. Now we can say that कि next point हम लोग बोल सकते हैं the hybrid orbital used by metal ion point in the direction of the ligand. Hybrid orbital used by ligands, that is metal ligand bond decide the direction of the geometry of the coordination compound. n-1d or n-d orbitals used in the hybridization allow the complexes to be classified as inner orbital complex and outer orbital complex. The type of hybridization decide the structure of the complex. So, steps to understand the metal ligand bonding include steps to understood metal ligand bonding. That is, first find oxidation number of metal. Central metal atom 2. Valence shell electronic configuration and right electronic configuration. उसके बाद में complex is low spin और high spin, ये भी पता चल जाएगा इस पे. And from this number of ligands find the number of metal orbitals required from the bonding, है ना. Number of ligands, find the number of metal ion orbital required for bonding. Required for bonding. और बोल सकते हैं हम लोग from the number of ligands we can identify from the orbital of metal ion available for hybridization. So type of hybridization can be involved. Identify The orbitals of, identify the orbitals of metal ion available for hybridization. So, type of hybridization involved can be identified. Type of hybridization can be identified. उसके बाद में determine the number of unpaired electrons and predict the magnetic behavior. उससे अपन number of unpaired electron predicts magnetic behavior. इस तरह से हम लोग उसका कॉम्प्लेक्स का इंटरनल स्ट्रक्चर, उसकी मैग्नेटिक बिहेवियर, उसके ऑर्बिटल्स और लिगैंड्स, मेटल ऑर्बिटल्स का हाइब्रिडाइजेशन, ओवरलैपिंग ऑफ लिगैंड्स, ये सब निकाल सकते हैं. नेक्स्ट लेक्चर वी आर गोइंग टू स्टडी detailed structures of these octahedral and tetrahedral geometries of the complexes.